In the last lecture, we introduced the basic notion of the subspace of a vector space. Let us recall what is meant by a subspace. We have a vector space V over a field F, and we have a subset W. Subset is a V, W is a subset of V, W subset of V is said to be a subspace of V if 1 it is non-empty, it should be non-empty, 2 it is closed under addition, that is x and y are in W implies x plus y is in W, and it is closed under scalar multiplication. That is, if x is in W and alpha is any scalar, then alpha x must be in W. If these are satisfied, then we say W is a subspace of V. We had seen some example last time. So, we will look at more examples of subspaces. The first example we had already seen in the last lecture. We shall see now another example. Let us look at the vector space V, which is the collection of all functions from S to R, where S is an arbitrary set, S is some non-empty set, and we are looking at the collection of all functions, real valued functions, which associate with every point in S a number in R. So, we are looking at all such functions. Now, let S naught be a fixed point in S, be a fixed point in S. So, we have S, we have S naught, a fixed point in S. Now, what we want to look at is the collection of all the functions which map S to R. So, they are functions from S to R such that at this point S naught, the value of f must be 0, that is f s naught is equal to 0. So, here is R, in the R the number 0 is there, we want all those functions f from S to R such that this S naught goes to 0 under f. So, this f s naught must be equal to 0. So, we are so W is the collection of all functions from S to R which vanish at S naught. The collection of all functions from S to R which vanish at the point S naught. Now, is W a subspace of the collection of all functions from S to R? Now, in order to verify whether something is a subspace or not, we have to verify three things. One, whether it is non-empty, whether it is closed under addition, and whether it is closed under scalar multiplication. So, the first thing to observe is that the 0 function takes every point to the 0 value, in particular the point S naught is mapped to the 0 value. So, the 0 function, which will denote by theta v, maps S to R is such that theta v of S is 0 for every S in S, and therefore, theta v of S naught is 0, and theta v is a function which maps S naught to 0, and therefore, theta v belongs to this collection, because this collection is a collection of all functions which map S naught to 0, and theta v is one such function, and therefore, W is non-empty. It has this 0 function in its collection. Next, suppose we have two functions in this collection. The fact that f is in W means it has the value 0 at S naught, and the fact that G has is in W means G is 0 at S naught. This means f S naught plus G S naught is 0. But by the law of addition of functions, this is the same as the value of the function f plus g at S naught. This says the function f plus g also vanishes at S naught, and therefore, f plus g is also in W. So, thus W is closed under addition. The next thing we have to verify is that W is closed under scalar multiplication. So, suppose we have a function f in W and alpha is any scalar. Now, our scalars are R, because f is the capital F of all functions from S to R is a vector space over R. So, our scalars must be R. So, take a function f in W and a scalar alpha in R. Now, since f is in W, it must take the value 0 at S naught, and of course, we are given alpha is R. And therefore, if I multiply f S naught by alpha, I will have alpha times 0, which is again 0. By the definition of scalar multiplication of functions, this is the same as the value of the function alpha f at the point S naught is alpha times the value of f at S naught, which is 0 from above. So, we get alpha f takes the value 0 at the point S naught. This means alpha f is also qualifies to be in W. Thus, whenever f is in W, alpha is in R, alpha f is in W, that says W is closed under scalar multiplication. So, thus we have W is non-empty, it is closed under addition, and it is closed under scalar multiplication. So, thus W is a non-empty subset of V, which is closed under addition and scalar multiplication. And these are the qualifications for something to be a subspace of V, and that says W is a subspace of F. Our vector space was F S R. So, the collection of all functions from S to R which vanish at that point S naught is a subspace. Now, we can generalize this. We can replace the point S naught by a subset of S. So, let S 1 be a subset of S. So, we have S and we have a subset S 1 inside that, and then we look at all the functions which map S to R. So, we have functions which map S to R such that if you take any point inside this S 1, it must go to 0. So, we are looking at all those functions F such that F S is 0 for every S in S 1. So, it is F S is 0 for every S in S. So, it is a collection of all functions, the collection of all functions, and what sort of functions are these? These are from S to R, and what else? They must vanish at every point in S1, which vanish at every point in S1, that subset. So, the subset at any point in that subset, the value of the function must be 0. So, we have taken, instead of a single point S naught, we have taken an arbitrary collection or arbitrary subset of S and looked at all those functions which it is in, and as before, this collection W is a subspace of F S R. We shall look one more example now from the context of matrices. So, let us take F any field and let us take the vector space V to be the collection of all m by n matrices. F m cross n means the collection of all matrices over F. Now, suppose A belongs to this vector space. To make things easier, let us take all square matrices. Okay. So, let us take the collection of all square matrices of size n by n. Take a matrix which belongs to this space. So, how does it look like? It is a matrix A11, A12, A1n, the ith row will be AI1, AI2, AII and so on AIN, and the last row will be AN1 etc. ANN, where the AIJs are all from the field F. So, we take an n by n matrix over the field F. For such matrices, we define trace of A as follows. We denote the trace of A by TRA for short. So, the trace of A is defined, this is the definition, to be the, just add all the diagonal entries A11 plus A22 plus ANN. So, it is just A11 plus A22 plus etc. plus ANN, sum of all diagonal entries. It is, we will come across trace later when we deal with matrices and non-homogeneous systems and so on and so forth. Now, let us look at this trace of A. It is easy to see that if we take two matrices A and B in F n cross n, then the trace of A plus B is the same as trace of A plus trace of B. This is because when you add two matrices, the diagonal entry of the sum is the same as the sum of the corresponding diagonal entries. Similarly, if A is an n by n matrix and alpha is any scalar, then the trace of alpha A is just alpha times the trace of A, because when you multiply a matrix by a scalar, the diagonal entries all get multiplied by alpha, and therefore, the trace gets multiplied by alpha. So, now we have this vector space of n by n matrices over F, and we now look at all those matrices which are n by n for which the trace is 0. So, we look at all those n by n matrices for which the trace is 0. Now, let is W a subspace. of f n cross n. Again, in order to verify whether something is a subspace or not, we have to verify three things: the fact that W is non-empty, the fact that W is closed under addition, and the fact that W is closed under scalar multiplication. Let us check each one of these. The first thing is, if you take the 0 matrix, the n by n 0 matrix, all the entries are 0, and therefore, the sum of the diagonal entries will certainly be 0. It has trace 0, and the moment a matrix has trace 0, it qualifies to be in W, and therefore, the 0 matrix belongs to W, which says W is non-empty. So, that is the first thing that we have to verify to see whether something is a subspace or not. The second thing that we have to verify is whether it is closed under addition. If A and B are in W, then the fact that they are in W mean the trace of A is 0 and the trace of B is also 0. If the trace of A and trace of B are 0, their sum trace of A plus trace of B will also be 0. But we just now observed that the trace of A plus trace of B is the same as trace of A plus B. So, trace of A plus B is 0, and therefore, A plus B is a matrix whose trace is 0, and therefore, A plus B qualifies to be in W. Thus, if A and B are in W, A plus B is in W. So, W is closed under addition. The next thing that we have to verify is whether W is closed under scalar multiplication. So, let us take A in W and alpha as scalar. The fact that A is in W again tells us trace of A is 0 and we have alpha is in F, and therefore, alpha times trace of A will be alpha times 0, which is 0, and again we just now observed that alpha times trace of A is the same as trace of alpha times A, and therefore, that is 0. So, alpha times A is a matrix, it has trace 0 and hence it qualifies to be in W. So, that says W is closed under scalar multiplication. Thus, we have seen that W, all these imply W is a non-empty, that is the first requirement, it is a subset of F n cross n, the set of all n by n matrices, such that it is closed under addition and scalar multiplication. And these are the qualities that are required for something to be a subspace, and hence W is a subspace of F n cross n. So, this is an example of a subspace in the vector space of matrices. Let us look at one more example. Take V to be R3. Our usual space, again the standard space R3 with which we always start all examples, and then now let us look at W to be the collection of all those vectors in R3, that means x is x1, x2, x3, such that say 2x1 minus 3x2 minus x3 is 0 and 3x1 minus 4 x 2 plus x 3 is 0. We are looking for all those vectors whose components x 1, x 2, x 3 are such that these two conditions are satisfied. We can look at W as follows. So, let A be the matrix 2 minus 3 minus 1, 3 minus 4 1. Then these two conditions boil down to saying A x is the 0 vector. So, we can write W as the set of all vectors in R 3 such that A x is theta 2. A is a 2 by 3 matrix. So, W can be thought of now as the set of all x in R 3 such that A x equal to theta 2 is W a subspace. Again we have to verify three things, that it is non-empty, it is closed under addition and it is closed under scalar multiplication. Clearly A times theta 3 is equal to theta 2. A is a 2 by 3 matrix, theta 3 is a 3 by 1 0 vector. So, the result will be a theta 2 2 by 1 0 vector, which implies that theta 3 qualifies to be in W, which implies that W is non-empty. The next thing to verify is that W is closed under addition. So, let us take x and y in W. The fact that x is in W means A must nullify it. Similarly, y is in W means A must nullify it, that is, it kills it. A x must be theta 2 and A y must be theta 2. If A x and A y are theta 2, A x plus A y must be theta 2 plus theta 2, 0 vector plus 0 vector is again the 0 vector. But matrix multiplication is distributive. So, this can be written as A x plus y is theta 2, which says that x plus y also get annulled by A. So, it qualifies to be in W. So, we have W is closed under addition. The next thing we have to verify is that W is closed under scalar multiplication. So, take x to be in W and alpha to be any scalar, and the fact that x is in W says A x equal to theta 2 and alpha is in F. But if A x is equal to theta 2, alpha times A x will be alpha times theta 2, which is theta 2. Again in matrix multiplication, constants can be moved and in and out of the multiplication. So, A times alpha x equal to theta 2, which says alpha x also gets annulled by A. So, alpha x also qualifies to be in W. Therefore, W is closed under scalar multiplication. So, we have seen that W is non-empty, is closed under addition and it is closed under scalar multiplication. All these say that W is a subspace of R 3. Now, we can generalize this. This leads us to certain subspaces associated with a matrix. We are going to look at a number of subspaces associated with a matrix, and these are the subspaces that are going to help us in the analysis of the various questions that we raised about a matrix, the systems of equations, diagonalization, decomposition, etc. So, we begin with F be a field and we look at a matrix which is in M cross n. Now, we can generalize the previous example and then instead of R 3, now we look at R n and look at all those vectors which get annulled by A. So, we look at the first subspace that connected with the matrix A is the following. We look at W to be all those vectors in F n such that A x equal to theta m. This is the same as looking at all the solutions of the homogeneous system corresponding to the matrix. So, this is the set of solutions corresponding solutions of the homogeneous system corresponding to the matrix A. So, we look at all these solutions of the homogeneous system, we would see that this is a subspace. It will be a subspace of what? It will be this is a collection of vectors from F n. So, this is a subset of F n. So, it will be if at all it is a subspace, it will be a subspace of F n. So, 1 clearly the 0 vector in F n is a solution of the homogeneous system. So, clearly theta n belongs to W since A theta n is theta m. Remember, A is an m by n matrix. If you multiply by the n by 1 0 vector, you get the m by 1 0 vector. This implies theta n is always, this is because theta n is always in a solution of the homogeneous system. Now, this implies that W is non-empty. So, that is non-empty, and if it has to be a subspace, it has to be closed under addition and scalar multiplication. So, let us look at x and y in W. What does that mean? Actually, we must say W is a non-empty subset of F n, because all we are for the definition of W, we are considering some vectors in F n which has this additional property. So, W is a subset of F n, it is a non-empty subset of F n. Now, suppose x and y are in W, because x is in W, A x must be theta m, because y is in W, A y must be theta m. Now, because both are theta m, their sum will be theta m plus theta m, which will be theta m. Matrix multiplication is distributive, therefore, A x plus y is theta m, that says x plus y belongs to W. This proof is exactly alike to the last example B sum. The next thing that we have to verify is the fact that it is closed under scalar multiplication. So, x is in W, alpha in F. So, we will go through this as in the previous example, which says A x equal to theta m, because x is in W and alpha is in F. That says alpha times A x is equal to theta m, alpha times theta m is theta m, and that says A of alpha x is theta m, and that says alpha x qualifies to be in W. So, thus we see that W is a non-empty subset of F n which is closed under. So, W is equal to the set of all x in F n such that A x equal to theta m is a non-empty subset of F n which is closed under addition and scalar multiplication, and that is what qualifies something to be a subspace of Fn, which implies W is a subspace of Fn. This subspace is called the null space of the matrix A. This subspace is called the null space of the matrix A and is denoted by N A. N stands for null space. So, what do we have? N A is equal to the set of all x in Fn such that A x equal to theta m. So, the null space is nothing but the set of all solutions of the homogeneous system corresponding to the matrix A. So, if A is an F m by n matrix, the null space is a subspace of Fn. So, that is the first subspace that we have seen associated with a given matrix A. Now, we shall look at another subspace which is associated with the matrix A. So, again we have A Fmn. When we were solving non-homogeneous systems Ax equal to b, we found that we may have a situation where for some b we will not have a solution, for some b we will have a solution. So, what we would like to do is collect all those b's which are good, in the sense we can solve the system Ax equal to b. So, we will now look at W. Now, where is this b? This b is in Fm, because A is Fm by n or m by n matrix, x is n by 1. So, the product will be m by 1. So, we are looking at all those b's in Fm such that there exists a solution x satisfying Ax equal to b. So, we are collecting all those b for which the system Ax equal to b is consistent. So, in the language of non-homogeneous system, we are looking at all those b's in Fm for which the system Ax equal to b is consistent. Now, W is a subset of Fm. Is it non-empty? Clearly, when we take b equal to theta m, we have the homogeneous system, and we know that the homogeneous system always has the trivial solution. So, therefore, clearly theta m belongs to W, because x is equal to theta n satisfies Ax equal to theta m. Therefore, W is non-empty. It is a non-empty subset of Fm, we will keep reminding that. Then we have to look at whether it is closed under addition. So, suppose B1 and B2 belong to W. What does it mean to say that B1 belongs to W? That means the system Ax equal to b is consistent. That means there is a solution x such that Ax equal to B1. So, there exists an x1 in Fn. Similarly, for B2 there is an x2 in Fn such that x1 is a solution of Ax1 equal to B1 and x2 is the solution of Ax2 equal to B2. Now, that says Ax1 plus Ax2 is B1 plus B2. Again matrix multiplication distributivity tells us A x1 plus x2 is B1 plus B2. Now, x1 is in Fn, x2 is in Fn, and therefore, x1 plus x2 is in Fn. Let us call it as x is equal to B1 plus B2, x belonging to Fn, x equal to x1 plus x2. Therefore, it says the system Ax equal to B1 plus B2 has a solution, and that means B1 plus B2 is qualified to be in W. Therefore, W is closed under addition. Similarly, we look at closed with respect to scalar multiplication. Suppose we will use consistent notation. Suppose B is in W and alpha is in F. The fact that B is in W guarantees that there exists an x in Fn such that Ax equal to B, and of course, our alpha is in F. Since Ax equal to B, we see that alpha times Ax equal to B, which in turn says A times alpha x equal to B. Now, x is in Fn, alpha is in F, and therefore, alpha times x is also in Fn. Let us call it as some y, Ay equal to B, y equal to alpha x belongs to Fn, which means the homogeneous system Ax equal to B also has a solution, namely the solution y. So, therefore, B qualifies to be in W, which says W is closed under scalar multiplication. Thus, what do we get? W is a non-empty subset of Fm closed under addition and scalar multiplication, and therefore, it qualifies to be a subspace of Fm. That says W is a subspace of the Fm, and this subspace is called the range of the matrix A. This subspace is called the range of A and is denoted by RA. So, what is RA? RA is the set of all B in Fm such that there exists an x in Fn satisfying Ax equal to B. It is all those B's for which Ax equal to B is a consistent non-homogeneous or homogeneous B0 is homogeneous system. So, RA is a subspace of Fm. So far we have seen two subspaces associated with the matrix. Let us say A is again Fmn, we have Fm here and we have Fm here. What matrix does is it takes a vector x in Fn and maps it to a vector Ax in Fm. Now, our null space Na is collection of all those vectors here which go and fall at the 0 vector here. So, how do we get the null space? To get the null space, what we do is we look at Fn, we look at Fm. In the Fm there is the 0 vector, and what we do is we collect all those fellows, we go and fall there, A times that becomes 0. This part is what is the null space of A. So, the null space of A is the collection of all those vectors in Fn which get mapped to the 0 vector. So, the null space of A is a subspace of Fn, because we are looking at those vectors in Fn which go and fall there. On the other hand, to get the range, what we do is we look at Fn, we have the Fm here. Now, we collect all those vectors B for which I can find an x here which goes and falls there. So, you can say B is the value taken by A at some point x. If you think of A as a function from Fn to Fm, B must be the value of the function A at some point x. So, that gives us the range of A. So, the range of A is the subspace of Fm, whereas the null space of A is a subspace of Fn. So, the net result is we have Fn, we have Fm. In general, A takes a vector x here to Ax, and some part of it is the one that taken to all the 0 vector, and some part of it here is the range of A, that is those B's for which solution exists for the non-homogeneous system. So, we have two important subspaces associated with the matrix, and one is in Fn and the other one is in Fm. We shall look at more examples of subspaces. Before we do that, let us recollect that if we have a vector space over F, and if you take a finite subset in V, then we looked at Ls, the collection of all linear combinations of S vectors, and this is a saturation limit we had reached at the construction, and this is what motivated us the definition of a subspace, and Ls is a subspace of V. This subspace is called the subspace spanned by S. Subspace spanned by the set S. Now, let us take a matrix A which is m cross n, entries are from the field F. So, I have m cross n matrix, and now let us look at the matrix A. Let us write it as A11, A21, etc. A11 is the first row, so it should be A12, A1n, and so on. The ith row will be AI1, AI2, AIN, and the last row will be AM1, AM2, AMN. Now, consider an m by n matrix and look at the first column. The first column has 1, 2, 3 m entries. So, if we now write C1 as the first column as a column vector A11, A21, AM1, we get a vector in Fm. It is in Fm because there are m entries here. Similarly, C2 is a vector A12, AM2, that is also in Fm, and so on, and in the nth column which is A1n, A to n A m n, that is also in F m. So, each column belongs to F m. These are called the column vectors of F. C 1, C 2, C n are called column vectors of A. Now, let us consider the set of vectors C 1, C 2, C n. This is a subset in F m, because each one of these vectors has m components, each one of the vectors is in F m. So, we have a subset of vectors in F m in the vector space F m, and that is a finite subset. So, we have a finite subset of vectors in the vector space F m, and the moment we have a finite set of vectors, we can look at Ls, the subspace of F m spanned by the S vectors. That is the set of all linear combinations of S vectors, but the vectors in S are the column vectors. So, linear combinations of the columns of A. So, we have the subspace of A m spanned by the columns of F m. So, what is this subspace? It is the subspace of all linear combinations of the columns of A. So, let us write it as, this is called the column space, this is called the column space of A, and we shall denote by, and we shall denote it by call A, column space of A. So, what is call A? Call A is the set of all vectors in F m which are linear combinations of the columns of A, where the alpha i's are in F for 1 to R. So, the column A, the collection of all linear combinations of the columns of A, it is the subspace spanned by the column vectors of A, and now we have to verify whether this is subspace or not, but we already know that Ls is always a subspace, and therefore, column A or the column space of A, which we denote by this, with what we call as the column space of A, is a subspace of F m. So, now we have got another new subspace, namely the column space of A. So, let us look at what have we got. We have F n, we have F m, and we have the matrix A, which belongs to F m n, which takes any vector in F n to a vector in F m. Now, here we got one subspace which we called as the null space of A. Here we had one subspace which we call the range of A. Now, we have got another subspace in F m known as the column space of A. We do not know what its relation with range of A. So, in general we will denote it like this. It may or it may not have an intersection with range of A, or it may not be different from range of A. At the moment we do not know. So, we do have a subspace in the range F m. So, in F m we have got two subspaces, and in F n we have got one subspace. Now, given the matrix A, we look at the matrix A transpose which is in FNM. The A transpose, you may recall, is the matrix which is obtained from A by writing the rows as columns and the columns as the rows. So, the ith row of A transpose is simply the ith column of A written as a row. So, A transpose is an so we can talk about the null space of A transpose, we can talk about the range of A transpose, we can talk about the column space of A transpose. Now, the null space of a matrix which was M by N, if you have an M by N matrix, the null space was a subspace of Fn. So, since A transpose is Fn cross M, the null space will be a subspace of Fm. And if you have a matrix which is M by N, the range is a subspace. If you have M by N, the range is a subspace of Fm. So, similarly, if I have a matrix A transpose which is Fn by M, the range of A transpose will be a subspace of Fn. And the column of A was a subspace of Fm. So, the column of A transpose will be a subspace of Fn. So, totally we have got 6 subspaces on the Fn side and the Fm side. What are the subspaces we got here? The null space of A, the range of A transpose and the column space of A transpose. Here we had the null space of A transpose and range of A and the column space of A. Now, the column space of A transpose is also called the row space of A, because the columns of A transpose are the rows of A, and similarly this is called the row space of A transpose. So, now we actually had 8 spaces, out of which 2 are identical. We end up with 6 subspaces associated with a matrix. 3 of them are on the Fn side and 3 of them are on the Fm side. There is a lot of relationship between these subspaces. We shall be looking at this relationship one by one. So, there are, if we summarize, there are 6 subspaces as of now associated with a matrix. 1, the null space of A, the range of A transpose and the column space of A transpose, which is the same as the row space of A. These are all subspaces of Fn, and then we have the null space of A transpose, the range of A and the column space of A, which is the same as the row space of A, and these are all subspaces of Fm. So, now we shall look at some relationship between these spaces. These subspaces. Let us begin with the column space of A. Suppose we have a vector B in the column space of A. What does that mean? This is true, something qualifies to be in the column space of A if and only if it is a linear combination of the columns of A. So, it must be of this form. There are n columns of A. So, B must be of this form. What does that mean? This means B is equal to alpha 1, the column looks like A 1 1, A 2 1, A m 1 and so on plus alpha n into a1 n a2 n am n. If you now write this, B is equal to a11 alpha 1 plus etcetera a1 n alpha n and so on am1 alpha 1 plus amn alpha n, which is the same as saying B is equal to Ax, where x is equal to alpha 1 alpha n. This means, since B is a linear combination, these alpha 1 alpha 2 alpha n must exist, which means there is a vector x such that B is equal to Ax. This is the qualification for a vector to be in the range of A. So, a vector belongs to the column space of A if and only if it belongs to the range space of A. Conclusion is the column space of A is the same as range space of A. So, for any matrix A, the column space and the range space are identical. Applying this to the matrix A transpose, we get that the column space of A transpose is the same as the range of A transpose. Now, we had the 6 subspaces, out of which 2 here collapse into the same and 2 here collapse into the same. So, eventually what we have got is on the Fn side, on the Fm side, we have range of A transpose, which is the same as the column space of A transpose, which is the same as the row space of A. That is the first subspace on Fn side. The second subspace on the Fn side is the null space of A. On the Fm side, we have the range of A, which is the same as the column space of A, which is the same as the row space of A transpose, and the null space of A transpose. Thus, we have 4 important subspaces associated with a matrix. Thus, there are 4 important subspaces associated with an m by n matrix, A belonging to F m cross n, 2 of which are subspaces of Fn and 2 are subspaces of Fm. Now, the analysis of these 4 subspaces plays a crucial role in the analysis of the matrix.